Okay, this is our last sample problem on determinants of matrices. This one's C23, and we're going to evaluate a 3 by 3 matrix. A little bit more complex than a 2 by 2, but it'll teach you kind of the algorithm for how these get done if they're larger than 2 by 2. So basically, it comes down to a row-column operation on a remaining 2 by 2 matrix. So we're going to pick the top row, and we're going to eliminate row and column each time I move across. So we're going to start with 1. 1 becomes the coefficient, and I eliminate 1's row and column. What's left is this 2 by 2 matrix, so I take 1 minus 0. That is, I calculate its determinant, so it's this coefficient, times the determinant of the remaining 2 by 2. So that's 1 minus 0. Next, I move across to 3. Every other term, in other words, these 4 right here, all get a negative sign on them. Anytime the matrix is larger than 2 by 2, for 3 by 3s and above, every other term becomes negative. So if these were negative, they'd become positive. If they're positive, they become negative. So as a coefficient, the 3 is negative 3 times. And again, if I eliminate this row and column, it's 4 minus 3 for the remaining 2 by 2. And then finally, plus, we're back to positive again, 2 times. Once I eliminate 2's row and column, I have 4, 0, 1, 1, so it's 0 minus 1. And if we calculate this, this is going to be 1 times 1, which is 1, minus 3 times 1, which is negative 3, plus 2 times negative 1, which is negative 2. So that's minus 5 plus 1, or negative 4. And negative 4 is the determinant of this matrix. You'll notice the determinant is always a scalar quantity. Okay? But that's not the only way to evaluate this. We chose the top row, but really you can choose any row or any column. Now let's do an easier calculation of this by choosing the bottom row. I choose the bottom row because as coefficients it doesn't get much better than 1, 0, and 1. So let's perform the same operation. 1. If I eliminate 1's row and column, it's 3, 2, 1, 3 left, so it's 9 minus 2. Minus, because again, every other term is negative, but it's going to be a 0, and a 0 coefficient's amazing. It doesn't even matter what the 2 by 2 is that's left. 0 as a coefficient is going to make the middle term 0. So I skip to 1 plus, we're back to plus again, 1 times 1 minus 12. And now when I evaluate it, this is going to be 1 times 9 minus 2, or 7, minus 0, plus negative 11. And once again, you can see we're at negative 4. Now, I showed you using coefficients from the top row and the bottom row. Can we do it with columns? Well, yeah, sure we can, and it works exactly the same way. The only difficulty with columns is you have to remember where the negatives go. And in the upper left-hand corner, it always starts with a positive, then it starts to alternate afterwards. So if I'm going to use the first column, then that 4 needs to be negative. So it's 1 as a coefficient times, again, the remaining 2 by 2 is 1 minus 0, plus, minus 4, and eliminating 4's row and column, it's going to be 3 minus 0. And then finally 1, and eliminating 1's row and column, it's going to be 9 minus 2. And so we see we end up with 1 minus 12 plus 7. And that is also negative 4. So no matter how you slice it, the determinant of this matrix is negative 4. And I can use any row and any column. All I have to remind myself of is where the negatives go. Finally, there's a simple way to do 3 by 3s that doesn't involve these coefficients and eliminations. It's kind of a brute force method. The only downside is it's a one-trick pony because it only works for 3 by 3 matrices. And that's to start by writing the matrix and then repeating its first 2 columns. And then what we do is this. We take downward diagonals starting with the principal diagonal of the original matrix. So we would draw a diagonal straight down here, and I take the product of all 3 numbers. 1 times 1 times 1 is 1. I do the next diagonal. 3 times 3 times 1 is 9. And the final diagonal, 2 times 4 times 0, and that is 0. Then I do the same with the reverse diagonals, except all of these become negative. 1 times 1 times 2 is negative 2. 0 times 3 times 1 is 0. And finally, 1 times 4 times 3 is negative 12. And now if I take the sum of all these numbers, 1 plus 9 plus 0 minus 2 plus 0 minus 12, what do you know? I still get negative 4. So for 3 by 3 matrices, this is kind of a one-trick pony that allows you to do them pretty quickly. It does involve a little extra writing in space, but it does remove the necessity of calculating all these 2 by 2s. The one downside of this is, again, you can't really exploit the fact that you've got zeros. Those zeros will in fact produce diagonals of 0, but it's not like you're choosing for it, it's just going to happen. Whereas strategically choosing particular rows and columns to act as the basis of these coefficients can significantly reduce your work. So while this is a workable method, there should be an easier calculation to find the determinant of a 3 by 3.